Welcome to week 5's final lecture. The topic of this lecture is Cauchy's criterion. As a quick recap, in lecture 2 this week, we introduced the monotone convergence theorem, a method of guaranteeing the convergence of a sequence when we don't know what its limit is to start with. In the past 2 lectures, we introduced the technical tools of the lim_sup and lim_inf, to which we will return later in this course. For now, the primary property of the lim_inf and the lim_sup is that if they both exist for a sequence and are equal, then the sequence must converge. We will use this fact to develop Cauchy's criterion in this lecture, which gives yet another method of proving the convergence of a sequence when we don't know what its limit should be. Let's get started. First, we will introduce a new notion. A sequence is said to be a Cauchy sequence if, for every epsilon positive, there exists a capital N, such that for any two indices beyond n, the difference of the corresponding terms x sub n and x sub m is no more than epsilon. This should be contrasted against the definition of the sequence being convergent. A converging sequence says that there is a fixed number, the limit, such that if you go far enough, the sequence gets ever closer to the limit. A Cauchy sequence says that if you go far enough, the remaining terms of the sequence will cluster together near each other with any pair no more than epsilon distance apart. So the notion of a convergent sequence captures the idea that eventually every term of the sequence approaches a known point on the real line, while the notion for a Cauchy sequence captures the idea that eventually every term of the sequence approaches each other. Thinking about it this way, it shouldn't be too surprising that the notion of the Cauchy sequence has something to do about convergence. The basic result about Cauchy sequences is that if a sequence is convergent, then it has to be Cauchy. Going back to the clustering picture I painted on the previous slide, this is not too surprising. If the terms of the sequence eventually become close to a given point, the limit, then pairwise, these terms should also become close to each other. Two terms cannot both be close to the limit without being close to each other. This last statement is in fact one way to understand the triangle inequality. Again, the triangle inequality essentially says that if 2 points are each close to a third point, then those 2 points cannot be too far apart. Having discussed why the result should be true, let's talk about its proof. For convenience, we again denote by z the limit of the converging sequence x sub n. Let epsilon be bigger than 0. Since the sequence is converging, there is a value n such that for all later indices, the term x sub n is no more than epsilon over 2 distance away from z. Notice that instead of epsilon, we used epsilon over 2 as the tolerance. This is because if 2 points are each some distance d away from a third point, the worst that can happen is for those 2 points to be on opposite sides of the third point, and the distance between them will be twice d. Or, if 2 points are inside a circle of fixed radius, the farthest apart they can be is the diameter, which is twice the radius. Here, the third point is the center of the circle. Since at the end of the day, we want to show that those 2 points are distanced no more than epsilon apart, we will artificially force them to each be no more than epsilon over 2 from the limit. And this is essentially what steps 3 and 4 of the proof say. That if n and m are any two indices beyond capital N, then their corresponding terms are each no more than epsilon over 2 from the limit, and so by the triangle inequality, their distance from each other is at most epsilon, which is exactly what we hope to prove in order to satisfy the Cauchy sequence definition. In the previous slide, we saw a condition that guarantees the sequence is Cauchy, or we saw that what can cause a sequence to be Cauchy. In the next several slides, we will talk about what being Cauchy guarantees. First, we claim that any Cauchy sequence has to be bounded. We can prove this in a similar way to how we prove convergent sequences are bounded. The basic idea of the proof is, if the sequence is such that eventually the terms all cluster near each other, then there cannot be a chance for later individual terms to go far away from the rest. And of any initial terms that may be far away from the eventual cluster, there are only finitely many. So we can conclude that the sequence must be bounded. In fact, to help us do so, we notice that the Cauchy criterion forces all the terms to be near each other. We can just choose one of the terms arbitrarily and call it the center. Using it, we can control how far away the rest of the terms are eventually. To make this rigorous, first, we can find capital N, such that for any pair n and m beyond capital N, their corresponding terms in the sequence differs by at most 1. This is just a definition of the Cauchy sequence with 1 playing the role of epsilon. Of the two arbitrary indices n and m, we can set n to be capital N plus 1. We can also let n to be arbitrary. The Cauchy condition means that fixing x sub capital N plus 1 as the center, all terms x sub m with m beyond the capital N will be no more than a distance 1 away from this center. And therefore, we see that adding 1 to our chosen center, we get a number that is an eventual upper bound. And subtracting 1 from our chosen center, we get a number that is an eventual lower bound. And now, using theorem 41, which we discussed in lecture 3, a sequence that has an eventual upper bound must also have a possibly larger upper bound, and a sequence that has an eventual lower bound must also have a possibly smaller lower bound. Since this sequence is in possession of both an upper bound and a lower bound, we know it must be bounded. And finally, we arrive at the big reveal of this lecture. It turns out that every real-valued Cauchy sequence converges. And so with what we have said earlier this lecture, that every convergent sequence is Cauchy, we see that in the realm of sequence of real numbers, being Cauchy and being convergent are one and the same. The advantage to using the Cauchy definition is that you only need to know how to compute the values of the sequence and do not need to guess the limit beforehand. This is because the condition for a sequence to be Cauchy only ever talks about the values of the terms themselves and not of any limit. The proof that Cauchy sequences converge is a bit less intuitive, so let me give an overview of what we aim to accomplish first before showing you the technical details. Our idea of proving that Cauchy sequences converge relies on our theorem on lim_sup and lim_inf. Remember previously we have said that a bounded sequence whose lim_sup and lim_inf coincide is a converging sequence. Now, as we know from the previous topic, that every Cauchy sequence is bounded. This means that if we can prove lim_sup of x sub n and lim_inf of x sub n agree, then we're done. One can approach this in two different ways. One can either show directly that the two values agree, or that one can suppose that the two values disagree and try to derive a contradiction. The proof for the convergence of Cauchy sequence in your textbook is of the first flavor. So, just to illustrate the diversity of methods, I am going to present the contradiction proof in this video. Before we start with the proof, if lim_sup and lim_inf are not equal, then one is bigger than the other. Now recall we have already proven the general fact that lim_sup must be at least as large as lim_inf. We did this at the end of lecture 3. So, if we try to assume for contradiction that lim_sup is less than lim_inf, well, there is an immediate contradiction right there. So the only case to check is to see what happens if lim_sup is strictly bigger than lim_inf. If this also gives a contradiction, we know that the only remaining possibility, that the two quantities are equal, must be what holds. Having explained the strategy, now let's get into the weeds. Recall that our goal is to show that a contradiction can be derived from the assumption that the lim_sup of our Cauchy sequence is strictly larger than the lim_inf. So we start by assuming for contradiction this relationship between the lim_sup and lim_inf. The Archimedean property of the real numbers then implies that you can find two numbers a and b with a less than b that is strictly between lim_inf and lim_sup. Since a is bigger than the lim_inf, which is the supremum of all eventual lower bounds, this means that a itself cannot be an eventual lower bound. All eventual lower bounds cannot be larger than their supremum. The condition of being an eventual lower bound says that one can find a capital index n such that all later terms are bigger than the number. So its negation that a is not an eventual lower bound says that for every index capital N, there is at least one later term that is smaller than a. Call this term x sub small n. In a similar fashion, since b is less than the lim_sup, it cannot be an eventual upper bound. And the statement that b is not an eventual upper bound can be written as for every capital index n, there exists at least one later term that is bigger than b. Call this term x sub small m. Combining the two, we find that small n and small m are both bigger than capital index n, and that their difference is strictly larger than b minus a. Remember that we have in order x sub small n is less than a, which is less than b, which is less than x sub small m. Now we are ready to contradict the assumption that x is Cauchy. For we have just shown that there exists an epsilon positive, which we will take to be b minus a, such that for every n, there exist two later indices small n and small m, such that their distance is greater than epsilon. I highly encourage you to pause the video here and pull out the usable statements sheet for this week, which has written on it a definition of Cauchy sequences, and check that indeed this statement given in step 6 is exactly the negation of the definition of a Cauchy sequence. And so with this, we have contradicted the assumption that X is a Cauchy sequence. I wish to mention at this point that this final theorem we just proved depends strongly on the fact that R is order complete. Let's take a look at the proof and see where completeness was used. First, in step 2, we used that R has the Archimedean property. We should remember back to week 2 lectures that the Archimedean property for real numbers is a consequence of its nature as an complete ordered field. Next, in step 3 and step 4, we used the fact that the lim_sup and lim_inf are defined as respectively the infimum of all eventual upper bounds and the supremum of all eventual lower bounds. The fact that the values lim_sup and lim_inf exist is entirely due to the fact that R is complete, and thus have the least upper bound and greatest lower bound property. In fact, this is one significant place where the proof can break. One example of how something can go wrong is this. Suppose you have a Cauchy sequence x sub n, each of whose terms are rational. The limit, however, need not be rational. And this can be seen as manifestation of the fact that the rational numbers q is not complete, and hence you cannot run the same argument as here if you just replace all the numbers by only rational numbers and hope to obtain a convergence sequence that converges to a rational number. Okay, that's it for this lecture. Until next time.